This lecture will review some of the material that we'll learn about Chapter 8, two-dimensional dynamics and circular motion. So we'll start with two-dimensional dynamics. And so a lot of the strategy is the same that we used in Chapter 6. So the first thing you're going to do is make a sketch or a drawing, and then identify your forces, right, using an interaction diagram or drawing a boundary around your object. Then you're going to draw a free body diagram. You're going to then take the forces from your free body diagram and apply them to apply them with Newton's second law, and you're going to split your x and y components. So we see here that we have our net forces in the x direction is equal to the sum of the forces in the x direction, and that's equal to ma in the x direction. And for y, we have the net forces in the y direction are equal to the sum of each of the forces from our free body diagram in the y direction, and that's going to equal ma in the y direction. And once we have these equations, we can solve for the acceleration in x and the acceleration in y, and that's separate. Then we'll do that separately. And then once we have that, then we can use the kinematic equations, where we have our position, our final position, and the equation for the final position in x, and the final position in y, along with the final velocity in x and the final velocity in y. And we just need to remember that our x and y components are independent. So next we're going to do an example problem. Okay, so we have this problem, a 2D problem, and this is a rocket. So we're launching a rocket, and the rocket is to gather weather data. The rocket has a mass of 30 kilograms, and it generates 1,500 newtons of thrust. And on a windy day, the wind exerts a 20 Newton horizontal force on the rocket. And if the rocket is launched straight up, what is the shape of the trajectory, and by how much has it been deflected sideways when it reaches a height of 1 kilometer? Because the rocket goes much higher than this, assume there's no significant mass loss during the first 1 kilometer of flight. Okay, so we have here our givens. So we see that we're going to start from a position of 0 in the x direction and 0 in the y direction. We're also going to start with initial velocities in both the x and the y direction. They're both equal to 0. We have a final y height of 1,000 meters, or 1 kilometer is 1,000 meters. Our mass of the rocket is 30 kilograms. The thrust, and so the thrust is the force upward, is 1,500 newtons. Our horizontal force from the wind is 20 newtons, and that's and then we're going to find the final x position, the horizontal position, if the rocket goes 1 kilometer in the y direction. So the first thing we do is we determine the forces on our rocket. And so we can see here in the free body diagram that we have in the y direction, we have the thrust force up, and we have the force of gravity. And notice since the rocket is accelerating upward, our thrust force is going to be bigger than our gravitational force. And then we also have drag, we're going to call it drag from the wind. And so that's to the right. And there's no balanced force, there's no other force in the x direction. So we're just going to have these three forces. So the first thing we want to do then is let's take these, let's see if we can move. So let's go here. And what we want to do then is we're going to take these forces and convert these to the components in Newton's second law. So if we just write down Newton's second law, we have the sum of the forces is equal to ma. And we're going to use component vectors. So with component vectors, all we need to do is write down the three forces from our free body diagram. So we have F thrust plus drag plus Fg is equal to ma. And we're going to use column vectors to split up these forces into the correct components. So if we look at our free body diagram, we can see the thrust forces in the positive y direction. So if I want to draw the column vector, I'm going to say it's a positive F thrust in the y direction, and the thrust doesn't have any x component. And then for our drag is in the positive x direction, so I'm going to put the drag here. And now for the force of gravity is in the negative y direction, so I'm going to put that here. And then we're going to have an acceleration both in the x direction and in the y direction. Okay, so let's start with our the x equation here. So this is my x equation. And so I'm going to bring that down here, and that's going to be d is the only term that's non-zero on the left side, and that's going to equal max. And then if I take the equation on the bottom, then I'm going to bring that down here, and I have that force of thrust minus Fg is equal to may. And so if I want to solve for d, so I can go over here, or sorry, solve for a, so ax, I divide the top and bottom by m, or the right and left by m, so I'm going to have ax is equal to d over m. And to solve for ay here, I'm going to divide both sides by m, and so I'm going to have ay is equal to force of thrust divided by m minus, now the force of gravity is mg, so I'm going to divide that by m. And so these cancel out, and so then ay is equal to the force of thrust over m minus g. And now I can solve for those values. So let's solve for ax first. So ax is going to equal, the drag force is 20 newtons divided by 30 kilograms, or this is going to be 2/3 Newton per kilogram. And that's really meters per second squared. And so let's change that to meters per second squared. And now ay is going to equal, force of the thrust is 1,500 newtons. My mass is 30 kilograms minus 10 meters per second squared. And so my ay is equal to 40.2 meters per second squared. So now I have an ax and an ay, and because and so what I'm going to do is use these with the kinematic equations. So I'm going to start here with my x final is equal to x initial plus vi x delta t plus 1/2 a x delta t squared. So x final, this is what I'm looking for, but I know the starting position is equal to 0 and my starting velocity is equal to 0. Okay, so I just know now that x final is equal to 1/2 a x delta t squared. And now if I want to find, I can use, in order to find, what I'm trying to find now is the y position. So I know the y position, and I'm trying to find t to be able to plug it in over here. And so what I think I'm going to do is use y final is equal to y initial plus vi y delta t plus 1/2 a y delta t squared. I know that the starting position is 0. I know the starting velocity is 0. So my y final here is equal to 1/2 a delta t squared. I'm looking for delta t, so this is what I'm solving for. I know y final and I know ay. So so my delta t squared is going to be, so I'm going to multiply both sides by 2 and divide both sides by ay. So I'm going to get 2y final over ay. And then my delta t is going to equal to 2y final over ay and take the square root. And so when I plug those numbers in, delta t is equal to 2 times y final is 1,000 meters divided by 40.2 meters per second squared, and I get delta t is equal to 7 seconds, about. So I'm going to take that 7 seconds and I'm going to plug it in up here. So I'm going to say x final is equal to 1/2, and this is 2/3 meters per second squared times 7 seconds squared. And so my x final is equal to 16.3 meters. So this is my final answer. The question also asks me about so on a windy day, the wind exerts, and it says, what is the shape of its trajectory? And by how much has it been deflected? So we found out how much it was deflected, 16.3. But let's think about the shape of the trajectory. So what it's asking me for is, what does this graph look like? What does y versus x look like? And one easy way to tell is I can determine the slope and see if the slope is a constant or if it's not a constant. And so let's look at the slope for a minute. My slope is equal to the change in y over the change in x. And so if I think about that, the change in y over the change in x, my change in y is just, I can say it's y final minus y initial, but since y initial is 0, then it's just y final. And the same thing is true for x. X final minus x initial, well, I know x initial is 0, so delta x is just x final. So I can say then that is 40, where is it? 40.2. So this actually will be delta y is going to be 1/2 ay delta t squared, and delta x is 1/2 ax delta t squared. Well, there's 1/2 on the top and bottom, and there's delta t squared on the top and bottom, and so my slope then is equal to ay over ax, and those are constant values, and so my ay is 40.2 meters per second squared, and my ax is 16.3 meters per second squared. And so what that tells me is that my slope is a constant. And so since that's the case, then I should get something that looks like kind of a steep line like that, right, for y versus x. Okay, so we're going to go back to our slides. Okay, so we've done that problem. Let's go here. So the centripetal motion activity, we're going to watch a couple of videos, and what we want to do is observe the motion for the object in each of the videos, and we want to draw a force diagram, and we want to see if there's a net force acting on the object, and is it accelerating. And notice when the string is cut for these videos, we want to notice what's happening. So we want to observe the object's motion. So let's start with this video. Okay, we're going to watch another video here. So one arm is spinning and the other arm has a penknife. Okay. And we're going to watch one more video. These are all examples of a centripetal force and circular motion. So this one happens fast. We'll probably watch it twice. I don't know if I can go back on that one. More time. Okay, so watching those, you can think about what happened. Um, And one of the things to note is that there were there was a tension force that was applied for the first two examples, and that tension force was towards the center. Let's look at this slide. So there was a tension force towards the center of the circle, and when it was cut, the ball moved in a straight line. And notice too, there was in the third video, there was the little container, and that provided a normal force towards the center of the circle, and that created the centripetal motion. There's also friction, so imagine if you were on a merry-go-round and standing on a merry-go-round and going around, that the static friction would be providing the force towards the center of the circle that allows you to go around. And then we also have we have gravity as a force that, if you think about satellites in orbit, right, then the gravity is providing the centripetal force towards the center of the Earth um, that causes that circular motion. And so a force is directed toward the center of the circle and acts in the role causing circular motion. And we can apply Newton's second law, where we say the sum of the forces are equal to mass times acceleration, and this is centripetal acceleration, and this is pointing towards the center. So we can have an object um, that imagine if we were spinning an object in the air with a rope, then we would have the force of gravity, and we would also have the tension force. But we could also, like we saw the person do in the second video, right? The rope was towards the center of the circle. So in that example, we would need the sum of the forces in the R direction towards the center, and we would also have the sum of the forces in the Y direction. So force of gravity would be down, and the force of the normal would be up. So we would have a second equation. But just for the centripetal motion, we're gonna use the force towards the center of the circle. And notice that for circular motion, we can say that the acceleration is equal to v squared over r. So that's the new equation that we're introducing in this chapter. And like I said, the tension, normal force, friction, and gravity can all provide that centripetal force towards the center of the circle. And the other thing to note is that the velocity of the ball going around the circle, if we think about velocity, is distance. So the distance traveled over time, then the distance traveled around a circle is just the circumference. So we get 2 pi r as our distance traveled, and then the time it takes to go around the circle once, is called the period. So the time to go around once is the period. So for if the gravitational force provides the centripetal force, or the force towards the center, then we know this force is equal to capital G, the gravitational constant, times the two masses, and then divided by r squared. And we see a picture here from Newton's Principia, and we can see that if we launch a satellite at a high enough horizontal velocity, that the gravitational force, centripetal force towards the center, will keep that object in orbit. Now, just some information about circular motion that you need to know. We know that angular position is measured counterclockwise from the x-axis. And so when we talk about angular position, we're talking about theta. So we can see the theta circled here. This graph shows really an object moving around in a circle. And so we measure theta from the x-axis, and the location of the particle, it's on the circle, so it's going around, and it's going to track out a distance that's 2 pi r if it goes around the whole circle. The radius here is r. The angle that it works through is theta, so it's going to go, if it went all the way around the circle, it would go from 0 to 360 degrees, or in radians, that would be 2 pi. And the distance that it travels would be along the arc length. So here we have s, and if it goes all the way around, it would be 2 pi r. And so one full revolution is 360 degrees, or 2 pi radians. Another thing that we need to know about circular motion is the angular velocity, and that the symbol for angular velocity is omega. And this is the change in the angular position theta versus time. So we can see in this little chart here that if our initial angle is theta I and our final angle is theta f, if we take theta f minus theta I, we get a delta theta, the change in theta, and then we put that over time, over our delta t, and we can find our average angular velocity. And if we want to look for instantaneous angular velocity, we're looking for the change in theta over the change in time, d theta dt. Our units for angular velocity are radians per second. The kinematic equations for circular motion are analogous to the equations for linear motion. So we can see that for angular velocity, we have the final angular velocity is equal to the initial angular velocity plus alpha, and that alpha is the angular acceleration times delta t. And these are pretty, these are almost identical, right? These two equations are identical. We can see our angular position is the same equation as our linear position, and we can see our final angular velocity squared. This equation is analogous to this equation, and so it's very easy then to remember how we can calculate them because they're the same as our linear equations. Remember that we can link angular and linear distance. So we see that s is our arc length, and if we wanted to calculate s, we can say it's r times theta. And that kind of makes sense because if I wanted to calculate our circumference all the way around, it would be 2 pi r. That would be our theta, 2 pi, and then r would be our radius. So s becomes 2 pi r, and theta becomes 2 pi for all the full 360 degrees in radians is 2 pi times r. Okay, so an object moving at a constant speed is executing uniform circular motion, and so the velocity of a particle moving around that circle, notice that the velocity is always pointing tangent to the circle, right? The velocity of any object on this circle is one circumference, so 2 pi r, over the period, the time to go around once. And so we're going to work next on this problem from example 4.9. So let's change to here, and we're going to go to example 2. And so here we have a 4-centimeter diameter crankshaft, turns at 2400 RPM, so rotations per minute or revolutions per minute. What is the speed of a point on the surface of the crankshaft? So here we can draw a circle, and here's our point, and we know this is rotating around, so it's moving like that. So we see we're given radius is equal to 2 centimeters, right? Because our diameter is 4. Our RPMs, so this is our something like our omega is equal to 2400 rotations per minute. And it's really not omega. It's omega, remember, is degrees or radians per second. So it's kind of something like that. So we'll just call it like omega squiggle because it's still talking about a rotation, which is not a distance. But what we want to do is we want to convert this to rotations per second. So let's do 2400 rotations per minute times 60 seconds in 1 minute. And we get 40 rotations per second. All right, so we can say then there's 40 rotations is equal to 1 second. And so if I want to find out the time it takes for one rotation, or the period, what I can do is I can divide each side by 40, and I get one rotation is equal to 1 second over 40. And so then if I do the multiplication, I'm going to get, or the division, I'm going to get 0.025 seconds per rotation. So that tells me for one rotation, it's going to take 0.025 seconds. So the period is 0.025. And now the question asks me, I forgot to write down the find, so find, let's see, find the speed of the point, so find v. Okay, so now that I have the period, I can find v because I can say the velocity is equal to the circumference, so imagine the particle goes all the way around one circumference, so 2 pi r over the period, t. And so if I plug in, I get 2 pi and then 0.02 meters. That's my radius, divided by 0.025 seconds. And my velocity then is 5 meters per second. Okay, so next we have Newton's second law for uniform circular motion. So we can see the net force is pointing towards the center of the circle, and the acceleration is pointing towards the center of the circle. I can see my velocity here is tangent to the circle. And if I want to find, so this is my free body diagram where I'm not showing the z component, or usually we talk about it, the y component. I'm not showing that here. I'm just showing the radial component. And so I've got the sum of the forces in the radial direction is equal to ma in the radial direction. And so I now can plug in my a, remember, is v squared over r. And so I can also use this equation, v is equal to omega r, and plug that in. And so I can use either one of these equations, mv squared over r or m omega squared r. And for the forces in the net direction, we're going to have that the sum of the forces is equal to 0. So we don't have any forces in the tangential direction for uniform circular motion. And then the last thing we're going to do is we're going to look at this problem. So let's go over here. And what we want to do is we want to analyze the vertical circle. So we haven't looked at a vertical circle yet, but we're going to look at a vertical circle and imagine a plane flying in a vertical circle and looking at the fighter pilot. So what forces are on the pilot? And so if we draw our free body diagram at the bottom of the circle, so the pilot is here, right? The forces are going to be, there's a force towards the center of the circle, and there's a force of gravity down. But since this the plane is flying in a circle, we know that this force, the force towards the center of the circle, has to be bigger than our force of gravity. And so that's what we see here. So if we want to look at Newton's second law, we're going to say the sum of the forces equal to ma. And we want to bring these forces from our free body diagram. We want to write the components. And so we have the force of the normal. So the normal force is the normal force of the seat on the pilot is what's creating that force towards the center of the circle. Minus mg, or force of gravity, is equal to ma. And so the normal force is going to equal, I add mg to both sides, that's going to equal ma plus mg. And so the force of the normal is equal to m times a plus g. And then for the pilot, when the pilot's at the top of the circle, we have the force of the normal of the chair pushing down on the pilot, but also the force of gravity down. So I'm going to have the sum of the forces is equal to ma. And so now I'm going to have the force of the normal plus mg, they're both in the same direction, is equal to ma. So the force of the normal is equal to, I'm subtracting mg from both sides, ma minus mg, or the force of the normal is equal to m times a minus g. And so the question asks us which, let's go back and see. So here in the bottom of the circle, my force of the normal is ma plus mg. And so the normal force is much bigger. So that means the chair is providing a big normal force on the pilot. And so the pilot, he or she is going to feel heavier down here at the bottom because the normal force is bigger versus the pilot, he or she here is the force of the normal, remember, is ma minus mg. So the normal force is smaller. So the pilot will feel lighter when they're at the top versus what the force of the normal at the bottom, which is bigger. And notice here on this example, we plugged in ma is mv squared over r.